Welcome everyone. We are very excited and happy to have you join our fourth Morocco AI webinar of this AI webinar series. A brief intro about Morocco AI and who we are. So Morocco AI is an initiative led by AI experts in Morocco and abroad. These experts are professors, researchers, and AI professionals. The mission of Morocco AI is to promote AI growth in Morocco and build a strong collaborative AI community, both locally and abroad. We seek to foster excellence in AI education, research, and encourage the innovative spirit. This AI webinar series aims to bring Moroccan AI researchers to present and share their work with the community. For today's webinar, I will be your host. I'm Iman Khouja, a Ph.D. student at Mohammed V University and International University of Rabat, working on LLP and its application to understand job market needs. Our last webinar tackled recent advances in medical imaging segmentation. If you have not watched it yet, please find the link in our website. For today's webinar, Ismael Lemhadri will present neural networks with feature sparsity. Ismael Lemhadri is a Ph.D. candidate in the statistics department at Stanford University, advised by Robert Tibshirani. Ismael completed undergraduate studies in France at École Polytechnique and worked at Google and Job Trading. He is the recipient of Monahan Foundation Ph.D. Fellowship and the Stanford Graduate Fellowship. If you have any questions during the presentation, please type them on the chat on Zoom or YouTube, and we will make sure to bring them up at the end of the presentation. And please be sure to stick around for our networking session right after the presentation, where we will break out in a smaller room so you get to meet and talk with some of the attendees. The presentation will last for approximately 40 minutes, followed by 10 minutes of Q&A. Without further ado, Ismael, please feel free to start when ready.
Thank you very much for inviting me and having me today here. I'm very happy to have this chance of speaking with all of you back home. This is my first time actually speaking to an audience in Morocco, and it's a privilege. So thanks again for giving me this chance. I actually grew up in Morocco. Then I moved to France about 5 years ago, or 6 years ago. I did my undergrad studies there, and then I moved to the United States for my PhD. And I've been working on my PhD for a few years now, and the talk that I present today is precisely about some of the research I've done at Stanford. I'll aim for the talk to have like you just heard, about 40 minutes. But feel free to interrupt me at any time if you have any questions, and I'll also stick around after the talk for a more informal discussion. So I'll go ahead and share my screen. And the topic of the talk today is about neural networks and about feature selection. This is joint work with Fang Ruan, who is doing his postdoc now at the University of California, Berkeley, and my advisor, Rob Tibshirani. And I'll start by just giving a bit of a background about what kind of topic we're tackling here. Looks like I got muted for some reason, sorry. I'm specifically interested in the kind of models we get to use with pretty large, massive amounts of data. And this is a figure that shows the kind of structure or just artistic picture of a convolutional neural network. That's the typical kind of model and architectures that are really popular for computer vision tasks. So there's been this computer vision competition where over the last 10 years or so, we've observed a dramatic improvement in the performance of the best performing method. About 10 years ago, the best methods didn't really rely on neural nets. Actually, they used more traditional kind of feature engineering, and kind of building very carefully crafted features and then plugging them into things like kernel methods and support vector machines. But essentially from 2012 with AlexNet and every year after that, the best winning performing method has been some kind of neural network. It's not always the same neural network. There's a lot of work that's gone into tuning the architecture and optimizing the training of the network to get to the results I'm showing. But the results we're seeing are quite simply amazing and very, very impressive. And that was a competition, but the results go far beyond competitions. There's all kinds of areas where we have a lot of promising research and progress being made, whether it's healthcare, drug discovery, and then recommender systems. These are all areas where we tend to make heavy use of neural networks for predictive tasks. And the common thread that unites all these areas is, and these other areas as well, is basically that they're data rich. We have the ability today to collect large amounts of data. It's pretty cheap and easy to do. And so we store those large amounts of data. We're not always confident what the signal in the data looks like. And so we'll sort of just throw a very powerful kind of network at it, and we'll have large computing clusters that allow us to optimize and train efficiently those networks. And eventually we'll end up with a trained model that's pretty good at learning the kind of structures and signals that are there in that data without knowing a priori what it really looks like. So the basic idea behind that is that we'll build a very large kind of model that can absorb any sort of signal. And even if we don't really know what the signal is, we won't really look or try to understand how it's doing, but we'll just be pretty happy with the performance of the network we get at the end. And this is also the case in this kind of classical setting. I showed computer vision problems, but there's other problems where the data is more structured that also benefit from having this strong predictive ability. This is an example of just what kind of data we would feed into these models. We have a number of observations. These are maybe different individuals for which we've measured some variables that we're able to collect. And then we have some outcome of interest that we're really interested in predicting. So the goal is to correlate those features which are available, which we can measure, with that response, which I shown in red in here, and to basically understand and ideally predict the response based on the features. For example, maybe the response here is the presence or absence of a disease. And the features are genomic measurements. We can go to the lab, do genetic tests, and that's kind of easy and relatively accessible, but we don't always have the ability to know whether the person has that disease or not. So we're really interested in being able to predict that based on the features that we have. And there can be huge sort of consequences if we can do that correctly, whether in biology, where we can basically predict disease early, and if we predict it right, then we can act on it, we can prevent the disease from developing further. And there's all kinds of other applications where having that predictive ability is a very powerful thing to do. But predictive ability alone is not enough. The reason for that is that we can't always trust a prediction if we don't know where it came from. So we're really interested in not only having powerful models that predict the response well, but would also like to have the simplest possible model that can do that. Neural networks are very good at the first item, performance, but they're not so good at that interpretability and simplicity. They're very complex methods. We have algorithms that train them, but we don't always understand what is it that they picked up from the data, where the signal is lying. And this is where feature selection comes in. Feature selection basically means out of this matrix that I showed here, to be able to just gray out as many columns as possible and to end up with a small number of columns that are the most predictive. So we're going to reduce not the number of observations here, but actually the number of features. And that's going to be very useful to reduce the complexity of the model. It can also be useful when actually measuring or collecting those features is expensive. If every single gene takes a different measurement, then collecting 10 genes, it can be much simpler and cheaper than collecting 1,000 genes. So if we can really nail down the set of important features and measure just those, and rule out all the other features that are there that we measured but we realize we don't really need, then we can gain a lot. Feature selection is also helpful when the model is complex to train, as is the case with neural networks, because we're reducing the size of the input. And so it's simpler to train. And of course, it helps with interpretability, because now I know that there's only these few features that are contributing to the model, and everything else is not going in at all. So I can basically focus on those few features, perhaps subject them to further study, and that helps with understanding what the model is actually using, what features are really the most important. And this is an example of a feature selection path. This is a protein data set, and we have these 80 or so proteins, 77 to be precise. And then we have some outcome, which is about these mice, whether they're healthy or sick, trisomic. And there is certainly a correlation between the expressions of these proteins and the outcome, which is the disease. And on this curve here, I'm showing the classification accuracy on this binary classification task for models with varying number of features. And we can see that with less than half of the total number of features, we can essentially recover the same accuracy as the best performing model. So the last 40 or so features weren't really useful or necessary. So we could just as well have stopped here using those 35 features that the model selected, and we would have gotten just as good of a performance. And if we're willing to lose a little bit more in terms of accuracy, then we can actually go down a bit further and keep reducing the number of useful features. Of course, eventually we'll end up with a very, very poor model that doesn't use any feature. And the sweet spot is somewhere in this curve. As a method, the method that I'm showing here doesn't really say what's the optimal number of features. That's sort of another question to ask, depending on the trade-offs that are at stake. But we have this entire curve, and from this curve, we get the information about how many features are needed, which ones are the most important, and how far can we get in terms of performance with just a few features. So, of course, feature selection is not a new research area. There's been a lot of work in prior literature. There's generally three kinds of methods. There's filter and wrapper methods. There's embedded methods as well. I won't go into too much detail about what each of these actually is doing, but I'll just say that embedded methods differ from filter and wrapper methods in that they perform both the feature selection and the prediction simultaneously. What that means is that I have a single model that I will train that will both find out which are the most useful or important features and actually come up with a prediction at the end. Whereas filter and wrapper methods tend to do just the feature selection. So they just report that these are the individual best features. And then that's it. So then maybe I would have to build a model down the line that uses those features, but embedded methods do both tasks at the same time. And the lasso is perhaps the most famous kind of embedded method. It's this linear kind of model with an additional penalty, this L1 penalty that penalizes the number of active features. And the lasso is a very famous, extremely popular method that has found a lot of usage in all kinds of areas where people now use it on a daily basis for understanding their data. Unfortunately, the lasso is limited in its scope and ability in that it's just linear. So the kind of signals that the lasso can capture, the relationships between input and the response, can only be linear relationships. But the truth is often non-linear. There's complicated signals in real data, and the lasso, for example, would not be able to capture that. So our goal today will be to go a bit beyond that and try to capture arbitrary sort of non-linearities, so much more complex kinds of signals. And at the same time, to achieve feature selection. So I will propose a method today that is an embedded method, so in that third category that I described, that will optimize over this large function class, so it can capture all sorts of signals. There's actually results about neural networks that say that if we allow the network to grow arbitrarily large, both in depth and width, and perhaps even just in depth actually, with just one hidden layer, we can capture any sort of signal. So it's really, really large, the sort of signal relationships between income and input and output that the function class can capture. And the way we will do that is using this kind of hierarchy principle that I will describe in more detail. But before doing that, I would like to actually share a little video that we have here about the method. So I'll go ahead and change screens here. I'll go to the LassoNet website, which is lassonet.nl, like machine learning. And just here, there's this kind of 2-minute video that we watched together. I'll try to actually have the sound on. If the sound is not working, let me know so we can fix it. Wow, my neural net for diagnosing cancer has 95% test set accuracy. My boss would be very happy.
Hi Ismael, how is it going?
Hey boss, it's going great. My new neural net has 95% test set accuracy.
Great. So how does it work?
It works like this. There are connections from each feature to the hidden layer.
But which features are important for this task? Our medical collaborators will ask about that. It won't be very useful unless you can answer that question. So let me know when you have an answer.
Maybe I should apply a lasso penalty to reduce the number of edges. Gee, that really didn't simplify anything.
Aha, I have an idea. I'll add skip layer connections and use their weights as upper bounds for the hidden layer weights. That way, I can encourage the learning algorithm to eliminate all of the weights for a given feature. Nice. This has reduced the number of features from 5 down to just 2. I can't wait to show my boss.
Hey, Ismael, you wanted to see me?
Yes, I have simplified the network considerably. Now, it uses just 2 features, and there is no real loss of performance.
Fantastic. Good work. I can't wait to show this to our collaborators. To say thanks, I'm giving you Saturday off, but I still need you to come in on Sunday.
Okay, that was our short 2-minute advertisement video for LassoNet. Before I continue further, are there any questions about what I've said so far? If there are no questions, I will continue. And before giving more detail about the method itself, I'll just show here the results on this famous data set, the digits data set called MNIST. And here in the top, I'm showing the classification accuracy by number of features. So here we actually see a strictly increasing curve because the accuracy tends to increase with the number of features in the model. The features here are just pixels, right? So the total number of features is actually 28 times 28, which is 784. That's the total number of pixels in this square. And the accuracy is very good on this kind of simple, very well-known data set. And in the bottom, I'm showing something that's actually a bit more interesting than accuracy alone, which is the active features and the most important ones. So basically, I'm overlaying a sample digit from a 5, a sample digit from a 6, and the task here is just to classify digit 5 from digit 6. So just this subset, this binary task. And I've trained this model that I've shown in the top picture. And now I'm interested in figuring out which features are the most important. So I have this model that's using just this small number of inputs, which is say 200 out of the 784. And I'm plotting here the individual pixel importance, which represents basically the importance of each feature. And we see results that are basically as expected, that we get to really discriminate based on those few pixels in the bottom left that basically differentiate from the 5 from the 6. Of course, a 5 and a 6 are pretty similar, but the main difference is that swirl that's present in the 6 but not in the 5. And that's what we find out in the method. So the most active features, and these are also the features that the method selected, are precisely those. So in this kind of example, we are able to visually recover what we might expect. There's some details here about what pixel importance means. And basically it has to do with the change in class probability. I won't go too much into the details of that, but we can take it offline, possibly if you're interested. And with that appetizer, I'll go a bit into the method and the idea behind the method, which is to use this kind of hierarchy principle. That's pretty classical and well-known in traditional statistics. The idea is to give prominence to the linear or main effects over interactions. And this model was introduced in the past for linear models and models with actually not neural networks, but models with interactions, which are just cross-product terms. And it's useful for interpretation and computability. And we'll show that we can actually also use it to achieve feature selection. What that means here is that we introduce this additional layer that I've shown in green here, that's purely linear. And we'll enforce a hierarchy between this green layer and the rest of the network. So we're given any kind of arbitrary architecture. We have our inputs, and we will modify the architecture slightly to add a so-called residual or just linear connection that skips the entirety of the network and goes from input to output. So if we just forget about the part in yellow and focus on the green, we just have a pure linear model. And now with this formulation, I've basically extended the neural network with this additional layer. So I have a model that's a sort of a hybrid between a neural net and a linear model. W here will just denote all the weights in the network, and theta denotes the linear connection. And with that new architecture being defined, I define the new objective function now, which is the sum of two terms and a constraint. The first term is the reconstruction loss, or mean squared error, maybe cross entropy loss. It just quantifies the predictive performance and the training performance. So the lower this loss, the better the fit of the model to the data. This is the standard kind of loss that any model, be it a neural net or other, will try to minimize to find the best possible choice of the parameters that fits the data as closely as possible. Then the second term here is this linear penalty. It's an L1 penalty on the linear weights of the network. And this penalty is precisely the penalty we find in the lasso, where there is no W, there is just the linear connection, and there is no constraint as well. So here, this penalty is what actually enforces sparsity. It has the benefits that as we penalize the L1 norm of the features, we will force some of the features to have value exactly 0. And so we'll only keep the non-zero values. But notice here that this L1 penalty only applies to the linear connection. But we have a highly nonlinear model, so we need to make sure that the sparsity we enforce actually applies to the entire network. And that is where the constraint comes into play. This constraint is over every single feature that I have. And for each feature, I am enforcing that the magnitude of the input layer weights, which were in this example here, these weights shown in black, with groups coming out of each feature, then enforcing that those weights, their magnitude, the maximum, the ad infinitum norm here denotes the maximum of the weights for each feature, are less than or equal in magnitude to the linear coefficient for that same feature up to some constant here. And the first consequence of this constraint is that the moment I enforce or zero out the linear coefficient for the feature, this right-hand term here will be equal to 0, and that automatically forces the left-hand side to be 0 as well. So that way, I only have to penalize this one single coefficient to actually end up penalizing the entire weights, the entire contribution coming out of that feature. And that is the sort of hierarchy that we are enforcing, because we're placing the linear term above anything nonlinear. So we end up with this model that has these two hyperparameters. The first one, it concerns the linear coefficient, is the same as the one we might find in the lasso. And there's basically an entire path that larger values of this penalty will penalize the linear coefficients more, and as a consequence, they will force more and more features to be zeroed out. Of course, when that penalty is equal to 0, then I'm not penalizing the model in any way, and it will just be using all of the available features. And then there is this additional hierarchy parameter that controls the strength of the linear and nonlinear coefficients. So by changing or turning that knob, we're able to have an entire range of models where in one extreme, where m is equal to 0, I'm actually forcing all of the nonlinear neural networks weights to be all 0, regardless of the value of the linear coefficient. So I'm basically just doing a linear model. And on the other extreme, where I'm setting that parameter to a very large value, I'm really trying to use as much of the network's contribution as possible in case where the signal is highly nonlinear. So we end up with this range of models. That's why I describe the method as a hybrid between a neural net and a linear model. The linear model is a model that we understand well, that's simple enough. The network itself is on the other opposite. And by having this range, we can basically tune and decide how much complexity to allow in the model. So that's the basic formulation of the method. Now that I've described it, I'll just, again, say that the advantages here are that we have this range of models. We have this all sorts of scales of linearity that we can decide on. That's one advantage. If the signal actually in the data has a lot of linearity, then we can pick it up easily. Maybe a kind of signal that a plain neural net would not pick up. And the other advantage is computational efficiency, because as I will describe in the next few slides, we actually have an efficient way of training this new, perhaps it seems complex, there's no obvious way to train it, but we have actually a fairly efficient way of training this kind of models. So this is what the algorithm looks like to train this model. We have some inputs that are the features and then some labels. We have a feed-forward neural network that can be, again, arbitrary. And we have a bunch of hyperparameters. Initially, I will start by training this dense network, and there's a number of steps in here. You might recognize here that I'm doing backpropagation, gradient descent, the typical kind of optimization for neural nets. And again, this is what the result might look like at the end when we've selected the features and looked at the classification accuracy. So everything so far seems normal. But I'd like to actually focus on two steps here that differentiate the training from standard neural network training. The first one is that we have this L1 penalty parameter, and there's a specific way of going over the path of that parameter. We don't necessarily know what value to pick for that one, so we'll have to choose. We'll have to basically train over an entire path and see what the path looks like, and then decide on a choice of model. And then to actually optimize it, we have this custom kind of operator that interleaves with every step of gradient descent. So gradient descent itself will go and sort of try to reduce the loss that I've shown here. But then to actually enforce sparsity, we need to add an additional step. And that's this custom operator that depends on the hierarchy that I formulated. So these are the two new ingredients. And it turns out that it's actually pretty important to do them in the specific way that I've described, where where the optimization involves increasing the value of the penalty. In linear models like the Lasso, it's usually the opposite. Actually, we start with large penalty, and we get a sparse model to begin with that uses just a few features. And then maybe we'll stop early along the way because we only care about the sparse region. But it turns out that for a neural network, that the setting is very different. The optimization here is more complicated. The objective function is non-convex. So we need to be careful about the way we do the optimization. And it turns out it's really important to get the model to work, to get a first good dense model that I'm showing in the second line here. And once that dense model has been trained, to slowly increase the value of the penalty. And essentially what that means is that I will start from this model that uses all the features, slowly increase the penalty, and then slowly remove features one after the other. But I will still do most of the training in the beginning for the dense model. And essentially removing the features just amounts to pruning. We have a good dense model that has high performance, and we're trying to just simplify it. So we'll only need a few steps of optimization along the path to converge. And we will be able to leverage the initial good solution and to keep using it along the path. So this is kind of the technical way the optimization is carried out. And I'm showing a scenario here on this figure with both strategies, right? One that actually starts by using a large value of the penalty and then slowly increasing it. So that goes from here to there, basically, from left to right. And we see that the test error is pretty large and doesn't improve in a meaningful way. Whereas going from dense to sparse, which means the green curve here, tends to result in much better performance. And there's explanations about this. We could possibly talk about it in more details if anyone is interested. Before I continue, just maybe make a brief pause here, because this was like the bulk of the method and the optimization. Are there any questions so far?
Could you, Ismail, wrap up in 5 minutes to move to Q&A session, please?
All right, so I'll try to wrap up then. Now that I've sort of presented the method, there is like the details of the optimization. We have a specific solver for this, and it basically uses so-called proximal gradient descent, where we end up solving this kind of problems, least squares problems that have this additional constraint. And we have an efficient way of doing that, that we basically derive from scratch, and that we're able to implement and integrate with existing deep learning frameworks, so that building this LassoNet optimization on top of existing neural networks only takes a few additional lines of code. So the computational overhead of doing this extra work that allows us to do feature selection is really negligible compared to the bulk of the cost, which comes from computing the gradients, doing the back propagation, and so on. And now that I've described how the method works and how the engine behind the method works, I'll talk a bit about the experimental evaluation, where we try to compare this method, LassoNet, with other methods. There's all kinds of other feature selection methods, and like I said in the introduction, most of them are not embedded. What that means is that they just output features, but that's pretty hard to compare. If I don't know the ground truth, then it's really hard to tell which features are really good. There's no ground truth here. There's just real data. So I need a fair ground on which to compare all the features. And to do that, I will take these existing methods that spit out their own selected features, don't necessarily spit out a prediction, and I will just use their selected features into other predictive models. And I'll use the same predictive models for all the methods so that I can really try to compare the methods just based on the value of the features that they output. And I'm showing here the results on this LassoNet dataset. That's a benchmark for feature selection that's been used in the past extensively in prior literature. And I'm comparing to a number of other methods that I mentioned in the introduction. The data here is speech data. So it's basically sound data with vowels and consonants. And I'm showing the number of selected features versus the classification accuracy for two separate downstream learners. One of them is a neural network, the other is a tree-based method. And I am showing this over a varying number of features. That goes anywhere from 25 to 125. And here, I basically used the output of LassoNet over the entire path. And then I did the same for the other methods. Most of the other methods actually take as input the number of features to select. So one hidden benefit of our method here is that we can basically train it over the entire path at a cost that is just the cost of training the initial dense model. Because remember, we were only pruning the dense model to reduce the number of features. But that's not how most other methods operate. So the computational cost here of the other methods really tends to scale, to increase with the number of data points here that we're evaluating. So that's another benefit of the method being able to go over the entire path. So the results overall are very encouraging because the method tends to perform highly in most cases. And I'll try to basically wrap up and leave it there. That was the kind of experiments that we did. We have all sorts of other extensions and possibilities. So I'll conclude by saying that I've introduced this problem of feature selection. I've shown why it's useful and how it sort of competes with just performance. And I've introduced a way to achieve feature selection for this large, very performant class of models, neural networks. The idea was to enforce this hierarchy between the linear and nonlinear components. Then I've described how to optimize this method over the path of features and using this crucial idea of dense to sparse optimization that proves this dense model using the custom operator that I introduced. And then I've shown some promising experimental results that reinforce the use of the method. There's a number of extensions and applications of the method. I won't go into too much detail about them because they can be fairly specialized. But there's ways of extending it for unsupervised learning tasks where we actually don't have an outcome, but just try to reconstruct the input, sort of using a bottleneck layer, using autoencoders to just compress and reduce the dimensionality of the data, and then try to reconstruct it. And that can be useful in other applications. We have other sort of problems that have to do with survival analysis, predicting the time that some treatment will take, or the survival times of patients. We have other problems that are useful for recommender systems, where we have to impute missing entries, where we have just a few observations, but not many observations. And we try to do that reconstruction, but using just as few features as possible. So these are all kind of applications. The last one here has to do with a specific kind of neural net that's used in computer vision tasks. I showed this MNIST example, but it's was just about selecting pixels. Often we have much more complicated images than that. We don't really want to select pixels. Maybe we care about other kinds of features to select. And that's another kind of application area. So I gave this little bit of an introduction about me. Maybe I can we can talk more in the breakout session. And I've also mentioned some of the extensions and future work, both about LassoNet and more recently, I've also been interested in doing what's called instance-wise feature selection, where we want to understand the model, but at a specific input, rather than understanding it in its globality. So I leave it here for today. Thanks for your attention. I put some of the links here for all of the resources that I've used.
Thank you, Ismail, for your great presentation and talk about LassoNet and your innovative approach to select features for neural nets. So it looks like we have a few questions, and if you have another question, please feel free to type them on the chat. So we have here, Ridwan is asking if we can say that LassoNet belongs to explainable artificial intelligence methods and how it compares with techniques such as LRP or line.
That's a great question. I've introduced the method as a feature selection method, and one benefit of feature selection is explainability. So it's fair to say that this is a method that can help with explainability. Now there's other benefits of feature selection, like I explained, that have to do with the computational power, computational cost of training, can also help with reducing overfitting, but certainly explainability is a useful and perhaps the most important reason for this. Now the other methods that I heard, like line, actually they tend to be on this so-called instance-wise feature selection. What that means is that they try to understand the model at a specific input. Say, if I'm given a specific patient, and I'm interested in just understanding which features are useful for that patient, rather than understanding how the model works in all of the data, because perhaps that patient is really special, and they differ from the rest of the data. So in that case, we would be doing instance-wise feature selection. So it's a kind of separate problem, but it's very related.
Okay, thank you. So I have here another question. So can LassoNet be used to find optimal number of features, or what other methods would suggest for that?
That's a good question as well. Usually, selecting the number of features is non-trivial and is a matter of trade-offs. In the curve that I showed in the beginning, maybe I can go back to it. We had this number of features, and then we had the performance on the left-hand side. So in this kind of curve, what does it really mean to be optimal? Well, it really depends on what sort of criteria, what sort of things we want to achieve out of this model. If we want to achieve the best possible performance, then perhaps the optimal number of features is around 35. But if we're more interested in, say, getting an accuracy that's larger than 0.6 and using the smallest number of features that allow to do that, then I would basically start from the y-axis, and I would realize that I need just about 10 features to do that. So in a case like this, depending on the question, there can be a different answer. In some cases, the answer is more obvious. There's ways to do cross-validation. The curve can look a bit different from this one. And then there's like a very clear answer to what the optimal number of features is. Say if the curve is like a U kind of curve, but that's often not the case with neural nets. And so there's no like notion of optimality here. But certainly we have the entire path and we can decide what number of features to use later.
Thank you. So I have here another question from another participant. He thanks you for the great talk, and he is wondering how this idea of skip connections in LassoNet is related to the same idea in ResNet when we try to optimize the number of layers.
I see. So in the first few slides, I had this kind of architecture where I'm showing just one single linear connection. And really the purpose of the linear connection in LassoNet is to, again, have a linear contribution to the signal, but even more so, to actually achieve feature selection. So we're not introducing any sort of linear connections inside the network. And that's the biggest difference with residual networks. Residual networks tend to really be a way of building networks that have good performance, whereas our linear connection is to achieve feature selection and only concerns the input layer.
Okay, thank you. We have another participant asking if LassoNet is packaged in a library and where can it be found?
Yep, that's a great question. Right now we have built a package in Python, and using it is as simple as basically installing the package from pip. We also have a link to GitHub with all the code, and it's implemented in PyTorch. We might have a version in other languages as well in the future.
Yeah, great. This is great. So also another question, how LassoNet can be extended to deal with images? Can we think of using KSVD, for example?
Okay, images. So the examples I've shown here, the only kinds of images I showed were MNIST, right? And there's more complicated kind of images than these. So that's a potentially more complicated topic because it's not clear what features do we want to select when we're dealing with images. Here I selected pixels, but in complicated examples, there is no sort of meaningful pixels to select because the images are not centered in any way and the pixels don't have any specific meaning. So it's in another entire area of research to sort of understand a bit what convolutional networks are actually doing. And that's an area of research that goes way beyond LassoNet because it covers all of computer vision, basically. But essentially, if we have good features, if we've figured out what sort of basis to use to represent the images, then we sort of know what features we want to select. And if we have that, then we could apply LassoNet.
Yeah, thank you. So for sake of time, I will just take two more questions. So we have here Mohammed asking if LassoNet does optimize the computation time, and if we use LassoNet, we can skip using powerful hardware for training models.
I see. So the way I would describe it is actually that it does not really improve the computational time. It just doesn't make it worse. And the reason for that is that we have to train a good initial dense model here to begin with. And that's another task that's difficult and complicated per se, that involves a lot of hyperparameter tuning and optimization. And that is actually necessary before using LassoNet. LassoNet can potentially improve later costs of the method when we have just a small number of features that are active. And then maybe we can store the model, maybe it's a smaller model for sure. But the cost of the optimization really is inevitable here. And that's really the price to pay to get a highly performant neural network. And that's not something that we will get to remove anytime soon, whether with LassoNet or with other methods.
Okay, thank you. So Asma is asking about the difference between feature screening and feature selection.
So, okay, it's mostly a matter of definitions and conventions. I didn't talk too much about feature screening because I focused on this embedded kind of methods in the first few slides. The main difference is that when we do feature selection, we actually want to use the method, the features for making a prediction later down the line. feature screening is a kind of way of just reducing the number of features, but maybe just as a pre-processing step. And then maybe we'll actually do some more reduction, or we'll train some other completely different model that's based on those. And feature screening is also a heuristic to improve existing methods, to sort of just try to improve on feature selection methods by finding a solution that's maybe suboptimal, but that's really easy to compute. So that's the sort of differences.
So thank you. We have still other questions, but for sake of time, we will move now to the breakout session. Thank you once again, Ismael, for your great talk. And we can now move to the breakout sessions. But before, I will just stop the YouTube live